Morning started a little late because we needed to give people a little extra time to register. I just want to mention that because hopefully the future of all the talks will start right on time. Okay, what I'm going to talk about today and tomorrow is the basic theory of elliptic curves. Now, Glenn actually covered a fair amount of that, so I'll just be doing a little more detail. Unfortunately, to cover the basics in 2 hours means I'm going to have to go fairly fast and not too many proofs, to put it mildly. But I hope this will give people the background they need to help understand some of the more technical talks later. Also, I'm going to completely ignore modular questions, which there'll be two other introductory talks on modular curves and their relation to elliptic curves. Okay, an elliptic curve is a pair consisting of a smooth projective curve E of genus 1 and a fixed base point on E. And one says that the elliptic curve is defined over K if the curve itself is defined over K, so it's given by an equation with coefficients in K, and the base point is rational. And the Riemann-Roch theorem says that one can embed such a curve as a smooth cubic in the projective plane, given in general by an equation of the form y squared plus a1xy plus a3y equals x cubed plus a2x squared plus a4x plus a6. The odd numbering on the a's has to do with modular questions, so I don't have to say anything about that. Where the point, this of course is just the affine equation. The point, the fixed base point here is the point out at infinity. If one is working over a field other than characteristic 2 or 3, then there's an easier equation. And one generally uses that, an equation of the form x cubed plus ax plus b. Or sometimes, some slight modification of that. The Frey curves are, I guess, a little more general. And equations like this are called Weierstrass equations. Now, the non-singularity of the curve E is equivalent, at least in this case, to the discriminant being non-zero, which for this curve is minus 16 times 4a cubed plus 27b squared. Doesn't vanish. There's much more complicated formulas, but they're easy enough to compute for the general form. And one also looks at the J invariant, J or J of E, which is 1728 times 4a cubed over 4a cubed plus 27b squared. The denominator not vanishing because of this condition here, of course. Okay. The reason one looks at this J invariant is the basic theorem that two elliptic curves are isomorphic, at least geometrically. So this would be over an algebraically closed field. If and only if they have the same J invariance. And that's an easy computation. Okay, there are two particular families of elliptic curves that get looked at a lot, so I just want to mention them. They're the curves which only have the x term, and these have J invariant 1728, and the curves which only have the constant term in the cubic, and those have J invariant 0. And there are especially examples of a special sort of curve, which I'll talk about later, maybe. All right. So that's the basic definition. One of the reasons that people look at elliptic curves is, well, they're more complicated than the projective line, which is the simplest curve. But they're simple enough they have a lot of additional structure. In particular, they have a group law on them. And there are a number of equivalent ways to define the group law. We'll just use this one. If you have 2 points on an elliptic curve, then the sum of those 2 points, r is p plus q, is the point such that the divisor p plus q is linearly equivalent to the divisor r plus 0. Again, Riemann-Roch shows you that there's a unique such point. That's useful for various purposes, but one can also write down explicit equations just to actually compute this group law. So let me just put a couple equations down. If p is xy and p prime is x prime y prime, then the x coordinate of the sum is given by y minus y prime over x minus x prime squared minus x prime. Of course, if you get infinity here, then it's the point out at infinity is the origin. And there's similarly formulas for doubling a point and things like that. Okay. I'll just also mention the additive inverse of a point, this point, is just you change the sign on the y-coordinate. I'm working exclusively on these simpler Weierstrass equations, just to make life a little easier. Now, it's a theorem, and actually, certainly in an elementary course, not so easy to prove that this actually gives you a group law, that either those formulas are, well, I guess it's not so hard to prove this does, but to prove the formulas give a group law, one has to check the associativity, which is a mess. But it's true. And once you have the group law, which is clearly commutative, so you have an abelian group structure, one can look at various maps on the elliptic curve. The most important map for our purposes is maps are the multiplication maps. So that's a map for any integer sending e to itself, which just takes a point and adds it to itself m times. If m is negative, you take the negative of that. And in some sense, all the arithmetic structure of the elliptic curve that we know of is either provably or conjecturally tied up with studying this map, and especially its kernel. But we'll talk about that a little later. Okay, let's see. That's the back one. The front one. Whoops. As you can see, I'm not an expert with these boards like Glenn is. All right, another map that sometimes comes up is a translation map. where if you fix a point on your curve, I'll call it tau sub q, which just sends a point to adding q. This is not a homomorphism, of course. It just sort of shifts things around a little bit. Now, on any curve of genus 1, Riemann-Roch theorem will tell you that there's, well, up to constant, there's exactly one holomorphic differential. So there's a holomorphic, except people usually call it the invariant differential. Invariant differential. Omega sub e, which for the Weierstrass equation, no, that was over there before I erased it, is just dx over 2y. On the general Weierstrass equation, it's dx over 2y plus a1x plus a3. So this even works in characteristic 2. The fact that the space of differentials is one-dimensional tells you that if you pull back, say, by translation, you'll get some multiple of it. In fact, you'll get the exact same thing. So that's why it's called invariant. One has the elementary fact that the pullback of this differential by translation is itself. Okay. So an elliptic curve is a non-singular curve of genus 1 given by, which can be given by the roots of a cubic equation. One's also interested in looking at these same cubic equations where there are singularities. Okay? So we need to look at singular curves. So that would be a curve y squared equals x cubed plus ax plus b, where the discriminant actually does vanish. That discriminant's the discriminant of the cubic, so that means there's at least a double root. So you either have a double root, in which case the curve has a node, so it looks kind of like that, with a crossing point here where you have two distinct tangent directions, or you have a triple root. And in that case, you end up with a cusp, which means it comes to a point. And these are what, as Glenn pointed out, these are called unstable. And this is semi-stable. Well, when you talk about reduction, I guess one says that. However, even when there's a singularity, if you throw the singularity away, the exact same rules, you can either use the formulas or you can use sort of generalized divisor class groups. The set of non-singular points, ENS, so that's the set of non-singular points, still forms a group. And in fact, the group's very easy to analyze. It's much easier than an elliptic curve in many ways. There are two cases corresponding to these two types of singularity. You either get the multiplicative group, GM, if there's a node, or you get the additive group, GA, if there's a cusp. And this is why one talks about additive reduction and multiplicative reduction. So there's, I guess, about 4 or 5 terms for the same thing. So cusp, additive, unstable, triple root, node, multiplicative, semi-stable, where the cubic has a double root. Okay. Okay, in addition to looking at one elliptic curve, one can look at maps between them. So a map between elliptic curves is called an isogeny. Which is a morphism that sends the 0 point to the 0 point. Maybe I should put 0 prime there for the other 0. And it's an elementary proposition that any such morphism is automatically a group homomorphism. Further, given an isogeny between elliptic curves like that, there's a dual isogeny going back the other way. Usually denoted phi hat from E prime to E, with all sorts of agreeable properties. The main property is that the composition gives you a multiplication map. See, this is going from E prime to E prime. So this is multiplication by m sub phi on E prime, where m sub phi is the degree of the map phi. And similarly, back the other way, phi hat composed with phi is multiplication on E. And it has all the sort of standard properties you'd expect of a dual. The one that maybe isn't so obvious, so maybe I'll just state that one, is that taking duals actually respects the group law on the elliptic curve. So the dual of the sum of two maps is the sum of the duals. Okay. Well, now, given any abelian group, such as an elliptic curve, one way to study it is to look at the self maps from the group to itself. Of course, since E is a variety, we'll look at maps that are algebraic, so we'll look at morphisms. So we can look at the endomorphism ring. End of E, which is just a set of isogenies from E to itself, where addition is addition on E and multiplication, as usual, is composition of functions. And one can analyze pretty well what this is. There's a theorem. The endomorphism ring of any elliptic curve is one of the following. It's either just the integers, where those are the multiplication by m maps for various m's. It's an order in a quadratic imaginary field. Or the other possibility, which people sometimes forget, it can be an order in a quaternion algebra. However, this last possibility is only in positive characteristic. So in some sense, it doesn't concern us since we're working over mostly number fields, except when we reduce mod p, of course, then it does. Such things will appear. In the second case, and I guess also the third case when you're working in characteristic p, one says that E has complex multiplication, or CM for short. And curves with complex multiplication have lots of nice properties that make them easier to analyze, so they're often used as test cases. And they're also useful for other things, as we'll see when there's a talk on Heegner points later in the conference. Okay, let's see. Okay. Now, as I said, the multiplication by M maps sort of contain all the, or almost all the arithmetic information on the curve. So in general, we can look at the points of finite order. So that would be the kernel of some multiplication by M map. So let me denote E of M to be the kernel of the multiplication by M map. So these are the points that have order M. And the torsion subgroup, try another chalk. The torsion subgroup of E is just a set of all points of finite order. And one wants to analyze what these look like. As always, before you can do any arithmetic, you have to analyze the geometry. So what do these look like over an algebraically closed field? Theorem. Over an algebraically closed field, well, if the characteristic of the field does not divide M or is 0, then you get a finite abelian group of rank 2. So Z mod MZ cross Z mod MZ. This is the one that will mostly concern us, although not exclusively. If the characteristic is P, say, greater than 0, then the points of order P, or more generally, the points of order P to the nu, say, there are two possibilities. Either you get a rank 1 subgroup, or you get 0. Okay. So you always lose something from the relatively prime to the characteristic place. You always lose one dimension there. And these are given names. This one's called ordinary, and this one's called supersingular. And the supersingular ones are the ones where the endomorphism ring actually turns out to be that quaternion algebra instead of something smaller. Okay. Unless I say otherwise through the talk, whenever I talk about E of M's from now on, I'm going to assume that M is relatively prime to the characteristic rather than having to keep writing that. And I don't know whether to follow Glenn's lead or follow what's in my notes, because I'm not sure what other people are going to do. I have my P and my L reversed from the way he was using them. But I think I'll do it that way. I tend to think of finite characteristics as P. All right. One also can fit together these M torsion subgroups by taking an inverse limit. So you can look at the, say, L to the nu plus 1 torsion, and multiplication by L gets you to the L to the nu torsion, and you can take the inverse limit of that. And one ends up with what's called the Tate module. In this case, the L-adic Tate module. TA sub L of E, which is the inverse limit. So it's just a coherent sequence of L to the nu torsion points, taking higher and higher powers of L. And just from this will be isomorphic to ZL cross ZL, the L-adics, after you choose some sort of basis. Let me just mention also, if anyone looks at the notes, it's the Tate module, the A here, of course, for Tate. Frequently, it's written TL in the literature, except that we're going to have Hecke operators that are written TL. So the A is stuck in there just to distinguish. Otherwise, you'd have TL acting on TL. The nice thing about the Tate module here is that this group is characteristic 0, right, rather than having Z mod MZs. And in fact, one often works with, one often wants to work over a field, so VL of V is the Tate module tensor Q, which is just 2 copies of QL. You want to think of that as a vector space, 2-dimensional vector space, which will be used as a representation space. So attached to an elliptic curve is a representation. I'm going to assume that the fields I'm working with are perfect here. So think of a finite field or think of a number field. So what do we do? Well, if you have an elliptic curve defined over K, then the torsion will be defined over K bar. The coordinates of the points will be algebraic numbers. So you can look at the action of the Galois group GK, which I'll write for the absolute Galois group of K bar over K, on the torsion, or on the inverse limit of the torsion on the Tate module. And this gives representations because this action will commute with the group law on E because E is defined over K, so the group law is given by equations with K rational coefficients. Okay? So this leads to a representation say rho sub M from the Galois group to the automorphism group of E of M, right, because it will move an M torsion point to another M torsion point. And this, of course, is just GL2 of Z mod MZ. So you get these 2-dimensional representations. Unfortunately, well, even if M is a prime, say, they're finite characteristic, though, of course, those will be very important. But one can also fit them together to get representations in characteristic 0. Okay, so take inverse limit of the representations, of the L to the new power representations, and that gives what's usually called the L-adic representation of E, or associated to E, which different speakers will probably have different notations for. Maybe I'll just write rho L, which contradicts that one. So this would be the automorphism group of the Tate module, GL2. And now you have L-adic coefficients. Or you could go to the, you could tensor this representation space by Q and get GL2 of QL, if you prefer. And one of the main tools that will be used, you see, is actually this yes, it's not here. Maybe to be consistent with Glenn's lecture. Why don't I put bars over these, if you'll permit me? What you can do is you can take this representation and you can reduce it mod L, not not really on the elliptic curve side, but thinking of ZL, you reduce that mod L, then you get Z mod LZ. In other words, you look at the representation onto just the L torsion points. So you go from an L-adic representation to a representation mod L. And it's the comparison of those two which sort of forms the heart of Weyl's proof. Okay, one thing I do want to mention, because it's useful at various stages, is although these representations in general are not so easy to analyze, one thing it is easy to determine is the determinant of this representation. Okay, so you're going into GL2, so if I take the determinant of rho L, that's a one-dimensional representation, so GL1 of QL. And that turns out to be is precisely the cyclotomic character. So people often write, it's the Tate module of the multiplicative group. The natural representation on that. This is just the L to the nth roots of unity. So it's the natural action of Galois on L power roots of unity. Okay. That's the back one. The points of order m, so the m torsion subgroup, this is a rank 2 Z mod mz module, has a natural pairing on it, which is usually denoted E sub m. From E of m, because E of m, to nth roots of unity, whose definition you can find in the notes, and it's even almost correct there, which is bilinear alternating. That is, it kills the diagonal. Look at all these things. Okay, it's non-degenerate. In other words, it makes E of m into its own dual. And it's also Galois equivariant. In other words, if you take an element of the Galois group of k bar over k, then you can apply that to this mth root of unity, and that's the same thing as applying the element of Galois to the 2 points, and then pairing them. These fit together, stick this here, fit together to give, similarly, a pairing, I don't know what to call it, EL something, prime, on the Tate modules. Which goes to the inverse limit of L to the nth roots of unity, which is, again, some ways more useful because you're in characteristic. These are modules over ZL, so they're characteristic 0. It works just the same. You just fit the E sub L to the new ones together. And again, it's bilinear, non-degenerate alternating and respects the action of Galois. Okay, that's largely, that's most of what I wanted to say about the geometry of elliptic curves. Pretty much everything I've said so far is about elliptic curves over algebraically closed fields or well, this representation, the curve's not over the algebraically closed field, but you're just looking at the fields where the torsion points lie. Now I'd like to look at some more specific arithmetically interesting fields. So let's start with finite fields. So suppose I have an elliptic curve over a field with q elements. Then the FQ rational points will form a finite group, clearly. One's interested in the structure of that group, or at least how large the group is. And for that, there's the estimate due to Hasse, which says that the number of elements in this group is more or less q plus 1. So q plus 1 minus that has a smaller order of magnitude, namely less than or equal to twice square root of q. And that's very useful for various things. These numbers turn out to be quite important, because what we'll do is we'll take an elliptic curve over a number field, reduce it mod p for various primes, so you get an elliptic curve over finite fields, and then you can examine these numbers as you take different reductions. But for now, if we're looking at one finite field, one defines the zeta function of E over that field to incorporate the number of points over, well, this bottom finite field and all finite extensions of that. So what one does, so it's the zeta function of E over FQ. It's a function, so T is the variable, is E raised to the sum over n greater than or equal to 1. You take the number of points defined over the field with q to the n elements. You divide by n. And you take t to the n. And you just multiply that all out as a formal power series. So this would just be a formal power series. It doesn't have any obvious pattern, but there's an unobvious pattern. Theorem that, in fact, it's a rational function. The zeta function of an elliptic curve over a finite field is equal to 1 minus a t plus qt squared over 1 minus t, 1 minus qt, for some integer a with absolute value of a less than or equal to twice square root of q. That's not a coincidence, of course. This number a is, in fact, exactly that q plus 1 minus the number of points. Yeah, maybe I should mention another way to state this is if you factor 1 minus at plus qt squared as 1 minus alpha t, 1 minus beta t, then alpha and beta both have, they're both complex numbers. I'm sorry? Oh, square root of q. No q. Thank you. Yes. So the absolute value of their sum is less than or equal to twice the square root of q by the triangle inequality. The other thing one can do is analyze the endomorphism ring of an elliptic curve over a finite field. And to do that, one uses the Frobenius map. So let me just remind you of Frobenius in this context, which I'll just denote by phi for the moment. And assuming that you write down a Weierstrass equation for the curve, it's just simply given by xy goes to x to the q, y to the q. One has the following proposition. The following are equivalent. First, the elliptic curve has no p torsion at all. And we're still working over a finite field. Second, well, the Frobenius map is clearly inseparable. You just have to stare at it. Remember that dual map. The dual of Frobenius is inseparable. The third condition is that multiplication by p is purely inseparable, which is fairly clear since this is just phi composed with phi dual. And the fourth one, which is the slightly surprising one, is that these conditions, which are clearly closely related, also determine, well, to some extent, the endomorphism ring. And the endomorphism ring of E is an order in a quaternion algebra. And as I mentioned earlier, I'm sorry? One is wrong? Oh, I'm sorry. Thank you. As I mentioned before, if these four conditions hold, if any of them hold, the curve is called supersingular, which is a horrible terminology because the curve's not singular, of course. It's a smooth curve. It comes from the original theory of complex multiplication. Those curves were singular because they were special. Okay. And the other thing I wanted to mention, yeah, otherwise, the endomorphism ring of E is actually an order in a quadratic imaginary field, order in and the various converses of 1, 2, 3 hold, in which case we say that E is ordinary. And just to give you an idea of the relative scarcity of these two types, almost every elliptic curve is ordinary. There's exact formulas. They're a little messy. May I just say there's approximately p over 12 supersingular curves over fp bar, okay, up to isomorphism. And in fact, they're all defined over fp squared. Okay, having discussed elliptic curves over finite fields, let me jump to the other extreme and talk about elliptic curves over the complex numbers. Here one has a very, very nice description in terms of elliptic functions. In fact, this is where the whole theory began in some sense. One can start with a lattice in C and look at the quotient of C mod the lattice, and that clearly forms a torus topologically, even complex analytically. All right, so that's one picture. The other way to think of it, if you like, is you take a fundamental domain and then you just identify those sides and identify those sides, and you glue it together and you get your torus. What one can do is look at functions, complex analytic functions, which are periodic for this lattice, the most famous being the Weierstrass P function. Which is defined as follows. P of z, or you might want to put L into the notation too. It's 1 over z squared plus the sum over the elements in the lattice other than 0 of 1 over z minus omega squared minus 1 over omega squared. I mean, the obvious thing to do is just to sum over everything in omega of 1 over z minus omega squared. That would be periodic. Formally, it's clear. Unfortunately, that sum doesn't converge, so you need these convergence factors. And once you throw those in, it's not obvious that it's periodic, but it is. It's easy enough to check. Okay. So we'll be using this. Also associated to a lattice are Eisenstein series, which one for each one for each integer, g sub k. And this depends on the lattice. It's not a function on the complex plane. Well, not that complex plane. And this you just sum the elements of the lattice, the non-zero ones, 1 over omega to the k. Of course, we do need to worry about convergence conditions, so you need k to be at least 2. So k an integer, k strictly greater than 2. And for odd values of k, it's clear that this is 0 just from replacing omega by minus omega. So it's really only the even ones that occur here. Let me just also mention there's a standard notation that little g2 is 60 big G4. And little g3 is 140 big G6. Which probably looks kind of arbitrary. All right. Let me get some more board space to state this theorem. The Weierstrass P function, since it's periodic, will give a map on C mod the lattice. One normally takes the P function and its derivative. So that gives a map from C mod L into, well, the affine plane, but they're poles, so it's really into the projective plane. And what this does is it defines an isomorphism to a certain elliptic curve, EL, contained in P2 of C. And the elliptic curve that you get is y squared equals Oh, I did put it in good. 4x cubed minus little g2 of L. This is why the sort of silly definition up there, the 60 capital G4 comes out in this formula minus little g3 of L. Whoops. X. This 4 here you can get rid of if you want to just make a linear change of variables. This is the classical way it's set up. And the discriminant here, maybe I'll call it delta of L, which little g2 cubed minus 27 little g3 squared is not 0, so we actually get an elliptic curve. Why does this look different from the other one? Well, it's because of this 4, and you need to change the variables. Okay. And this is actually an isomorphism of, well, these are the C points, of complex analytic Lie groups. The flip side of it, I'm going to call this A, is that B, every elliptic curve defined over C is isomorphic to some E sub L. In other words, you get every elliptic curve by taking some lattice. Oops. And one of the consequences of this, which I think Glenn actually mentioned, is that, for example, you can figure out what the M torsion looks like on any elliptic curve defined over C, because the group structure on this is very, very nice. It's easy to analyze. What's the drawback of this map? The drawback is that it's given by complex analytic functions, so you lose virtually all arithmetic information. Okay? So you can't take rational points here and expect them to go to rational points there. Okay. All right, so a lattice L is just a free group of rank 2. So if we choose a basis, it would look like z omega 1 plus z omega 2, say. But it turns out that homothetic lattices give the same elliptic curve. So E sub L is isomorphic to E sub CL for any non-zero complex number. Okay. So that means it's possible to sort of choose a normalized lattice rather than an arbitrary one. So we can take lattices, called L sub tau, the form z tau plus z, with tau in the upper half plane. Okay. Just by multiplying through, divide by omega 2, say. And then there's a natural sort of isomorphism. You see, the fact that this L sub tau contains the integers means functions will have Fourier expansions. It's very much like what Glenn was talking about. So there's a natural isomorphism here that sends a complex number z to a number I'll call u, which is e to the 2 pi I z. And it will map to C star mod all the powers of q, where q is e to the 2 pi I tau. Okay, oops, getting tangled here. Now later we're going to do this over non-Archimedean local fields. So I'd like to finish by just mentioning that the various functions that I've put up have analogs. You just change variables from z and the lattice to u and tau and q. So if we write u is e to the 2 pi I z and q is e to the 2 pi I tau, then the Weierstrass P function at z, with respect to that lattice, the L sub tau lattice, looks as follows. I'll put a 1 over 2 pi I squared in front here just to normalize things. It has the following expansion. Squared plus a 12th minus 2. So the thing to notice really is that all of the z dependence is in here. The rest of that's just a constant reflecting the particular Weierstrass equation. We also have the discriminant function for the lattice L sub tau has the following, well, first it's 2 pi to the 12th times a series n greater than or equal to 1. And here I'm going to have to apologize. The standard thing to use for the coefficients is tau of n, q to the n. So I don't, well, what shall I do? Maybe I'll put a triple underline under it. Tau of n. These are integers. This is the Ramanujan tau function. See, the problem is there's this other tau floating around. And this has the following beautiful product expansion due to Jacobi. It's q times the product of 1 minus q to the n, oddly enough, to the 24th power. And finally, the j function of the elliptic curve corresponding to this lattice, or the j function of the lattice, looks like 1 over q plus summation, say, c of n q to the n, where again the c of n's are integers. Okay? And the thing to note here is first there's this 1 over q in front. So if q is small, it will be large. And the second thing to notice about both of these is that you get these q expansions with integer coefficients, or, well, modulo a slight normalization problem. Okay. Well, I think I'll stop there. And during the second lecture, I'll be talking about local fields and global fields and various conjectures and theorems known there. Thank you. Question, yeah. I'm sorry? Elliptic curves, huh? The upper half plane usually has a non-Euclidean geometry. Why don't we talk afterward, okay, rather than in front of everyone? Okay.